Social distancing, you say? The future is watching. Welcome to Opcode Virtual Summit.
Hi, and we are back. So let's continue with our next speaker. So let me check this thing here. I guess for next time we probably need at least like 3 screens to get yeah. Can you hear me, Joxean?
Yes, I can.
Okay, perfect. Yeah, so we're running a bit early, so we can start now if you're ready.
As you want.
Yeah,
I
perfect.
don't have any problem.
Awesome.
Okay, give me 2-3 minutes at max because I want to close and finish one easy thing about is for the demo.
Okay, I guess we can do that then.
Come on. Yeah. Where is it?
Cool. Okay, I guess yeah.
Okay. Chart. Where is it?
Cool. So we will have our next speaker, as you have heard, like in a few minutes. And yeah, that's pretty much it. So like I was saying at the beginning, but I don't know if you guys heard, because of the sound issues at the beginning. But yeah, the conference very likely is going to happen at least once a month, depending of how successful this edition is. And yeah, so the idea is like instead of doing like a 2-day conference that would be like physical, is to kind of like shift that perception and just making it shorter. So it's gonna be like few talks, so around the alpha day, so people can watch it like if they're in Europe, like in the evening or late afternoon, and if people are in California, they can still watch it in the morning. And this is the best way to cover like multiple time zones. And instead of having something like which is like too long and takes too much time, we just have like alpha day together. If there is any topic you would like to see in the next edition, don't hesitate to make a suggestion in the chat. And the call for paper, I think, is probably going to be the same link anyway, so feel free to apply for it. And yeah, then your talk may also get selected for the next edition. So I guess we are almost ready for the next talk. And let me unmute. Yeah, can you hear me now?
Hi. Yes.
Cool. Okay, let me just move your screen. Tac.
Yeah. Can you see the presentation?
Yeah, no, we should be able to see it. Yeah.
Okay.
Yeah, all good. Yeah, you can start whenever you're ready.
Okay, perfect. So good afternoon or good morning, depending where are you. So I'm going to talk about a project I've been writing since last year. The talk is about how to recover as much as possible source code that we can compile by just clicking a button or running some script. So I will first talk about what is the problem that I wanted to work, what is the idea that I did and what I'm working right now, the prototype that I have, that I will have to drop and rewrite again because it is a prototype, and then talk about the future of this idea and about the tool that I want to write. So first of all, the problem. Often, for so many reverse engineering tasks, we need to extract pieces of codes from binaries to copy in source codes. It can be either simply global tables or something like that, for example, for encrypting algorithms, or it can be wall algorithms, or it can be many functions at the same time that we want to extract and put in our project for whatever reason. Some reasons that come to mind are, for example, compatibility, copying decryption routines from malwares, which is pretty common, doing recovery or reconstruction of lost source codes, or half automating porting of codes written in assembler to high-level languages. I know, for example, groups, the people that are trying to rewrite in higher level language, like in C, C++, old games that were written purely in assembler using Ghidra the compiler. Well, such a tool could help these guys. So, for example, talking about compatibility in this case, what I mean is, let's say that we want or that we need to be compatible with some commercial software that is only available in binary form. So we do reverse engineering of that obscure algorithm that the software is using for that specific or rare file format that they invented. So what we can do is, after we reverse engineer it, we can either implement everything from zero by writing specifications from the reverse engineered piece of software, and then from the specifications write code. This is commonly done, or we can directly use portions of that commercial software directly into our software. Yeah, it doesn't sound very legal, but I'm ignoring legality here because legality is depending of the country where you are. And when we are talking about compatibility, it is even more fuzzy than it usually is. So I'm just ignoring it. And also because regardless of legality, it is business as usual in many areas. For example, antiviruses or commercial game cheats do it all day. So, for example, one of the samples that I said, copying decryption routines, is very common in the anti-malware industry to just copy even verbatim algorithms from malwares, for example, from a file infector, after reverse engineering them. Indeed, I have done this myself when I used to work for one antivirus more than once. So manually rewrite from assembler to C some routines that this some disinfection or whatever, and then write AV plugins with these functions that I wrote directly from assembler to C after cleaning this or that for some specific file infector. Like, I don't know, in my case, it was Sality back in the day. And I know people that have even directly copied raw assembler and put it in ASM blocks in their C, C++ files. Please don't do that ever. And if we are talking about legality again, well, I don't think that in this case, for example, malware authors are going to complain about their intellectual property being used anywhere, I guess. This is the top idea, or why I really wanted to write such a project, which is recovering or reconstructing lost source code. This is one of the top 10 most common reverse engineering tasks, I will say. And also, I believe that it is one of the top 5 most tedious reverse engineering tasks. So one example, let's say that we have some company that produce some specific software for some specific industry. Due to a disaster, that company loses all or part of the source codes for that specific software. So that company contracts reverse engineering services, so the reverse engineers can reconstruct from the binaries they distribute to customers the source code. This is more common than what you might believe, and you might think about it only happening to small companies, but it happens to all companies all around the world. It might happen to big companies and to small companies. I have histories about both of them. Well, with a bit of luck, in that case, for the reversers, they might be lucky enough to have some version with divine symbols, with like, I don't know, dwarf or PDB files, so they have more information. But in most cases, you will have just raw binaries distributed to the customers. And it can be even worse. It can be even with some software protection measures, so you have to first crack the software. In this case, I'm totally ignoring also this example where the reverse engineers first have to crack the software. We consider that the tool that I'm going to talk about is when you already have reverse engineered your software and you want to start reconstructing the source code out of it. Okay, so there are other examples that I could talk about that for which we will need to extract some pieces of code from binaries to copy in our source code, but I think these are some good examples. So right now, the only part of the solution to this problem, and what we all do, is the following. We reverse engineer the software, whatever is our target, then we discover structs, enums, function names, etc., etc., and then we copy and paste directly from IDA or Kitra to our source code. We adapt the code and clean a lot of the stuff, and we make it compilable for our specific project. Well, it can be done this way for small parts or for when we are copying, say, a couple of functions, something like that. But for big codes, let's say that we are recovering a full, I don't know, management application. That's not going to work. It's not feasible. Cannot start copying this function in this function in this another file for, say, maybe 1,000 files difference that we shall have for compiling back to that management application. That's not practical. So this is my idea. The solution to the previous problem is obvious. I say it's obvious, not easy. So we just need to write a tool that automates most of the tedious and boring routine tasks. We should make it interactive because this is my experience, but most of the tools that I have been written for reverse engineering, when they are interactive, the reverse engineer can interact with them. They are better than purely batch tools. So in this case, we need interactivity to fix whatever the tool, whatever mistake the tool makes or whatever wrong guess it makes, because we are not going to write a software that makes better guesses than a human. And we actually need the human to verify that whatever the tool did was correct or not. Also, we want to allow incremental changes, even when such a software, in my mind at least, is meant to be used when you are mostly done reverse engineering your software. You want to fix the stuff incrementally. Let's say that we have some function names and some variable names, but then after we are working with that, we realize that one of the function names that we assigned was wrong. We just want to change that function name in that specific source code file it belongs to. We don't want to rewrite the whole project again. Also, we want such a tool to be integrated with the de facto reverse engineering tools, which are IDA and Ghidra right now. And, well, maybe after that, profit from the tool. So, yeah, it sounds easier than it really is, but it isn't either that hard, in my opinion. Actually, I don't really consider it a pure reverse engineering problem, but more of a software engineering problem, because we are not, for example, searching for classes and the hierarchies in binaries, which is actually a pure reverse engineering task. We are just going to output compilable source codes using the compilers, using hints from and interacting with the reverse engineer. Roughly, this is all we are going to do. So this is always in my opinion, okay? So what such a tool should do in my opinion? First, find functions and the correct prototypes. Probably the reverse engineer wants to fix them. Find local and global variables. Probably the reverse engineers want to fix the types or the names, etc., etc. Finds import functions and the corresponding header and library files. Like say, if we say that our target is used calling fopen, fclose, whatever, or I don't know, cout, we know that we have to do import stdio or import iostream, etc., etc. Also, we need to find the source files in the binaries. I don't want to have a huge C or C++ file with, say, 10,000 functions. No, I want to recover from the binaries something that is as closer as possible to the original source. How do you do that? You need to find what looks like where the original source files, and then split the functions in the single binary we are working on to the specific source files it belongs to. Last but not least, we need to find the hierarchy of structs, enums, functions, globals, etc., and just write the source code files. Yeah, it sounds more easier than what it really is. So some disclaimers before I start. First, I'm only talking about C programs, just plain C programs. I'm not talking about recovering something like Visual Basic, Go, Delphi, you name it. I'm just talking about C programs. Also, during this talk, I will only consider the tools IDA and Ghidra. And the reason is that, well, these are the only two reverse engineering tools that they have on the compiler of their own. That said, let's continue. So, I repeat again, let's assume that we are just talking about C programs. The first thing that we have to do is finding functions. It is easy, okay? We can just use the APIs of IDA and Ghidra. We might need to manually find and create some functions that IDA or Ghidra didn't find. This is especially true when talking about reverse engineering embedded devices, where most of the functions aren't ever usually, better said, discovered by IDA or Ghidra, and we have to write our own scripts to find some more functions. And also, finding functions is not a very easy problem because distinguishing between data and code is not trivial. Anyway, nowadays, most tools, or these two tools, IDA and Ghidra, work pretty well in most of the cases. Also, we need to fix the function prototypes, which is one of the areas where the compilers really fail a lot. So many times, the calling conventions, the number of arguments, the types especially, are wrongly guessed by the compilers. That's normal. I understand it. It's not an easy job, and it's not something that can be, in some cases, it's not something that can be statically determined. But it is fine. As long as such a tool for recovering source code is interactive, we can just interact with the reverser, and the reverser can just simply change the function prototype in either IDA or Ghidra, and that's it. Yeah. So there are many cases, however, where functions can be missed or the boundaries wrongly guessed. Some examples are virtual functions, jump tables, many different switch idioms, self-modifying codes, on-the-fly generated code, function tables exported by external libraries, etc., etc., etc. So we cannot write a tool that works in all of these cases. It is pretty much impossible, but we can focus on a tool that might work in the general case, and maybe, if it makes sense, tomorrow enhance or improve it later. So, another part, finding local and global variable. So this might sound easy too, but it isn't either. So variables are in a concept that exists, as far as I know, in most CPUs. So we don't have a concept of variables in Intel 86 or in AMD 64 or in ARM 32. They are just memory areas. We need to apply data flow analysis to find them and to find the alias. For example, in a white paper written by Ilfai Kilfanov called The Compilers and Beyonds, there is a specific part talking about this, how to discover variables, which is called variable allocations. And in Ilfai's words, he says that only that part is worth a separate paper. This is the specific part which Ilfai Kilfanov says so about local variable allocation. Fortunately, however, in many cases, for most of multiple targets, finding local variables isn't that hard, and that's not our job in most cases anyway, because it is the job of IDA, Ghidra. We just really need to fix things like assign proper types, map some variables that might be duplicated if we feel like doing so, etc., etc. Finding global variables, however, is usually more easier. We just quote just needs to find references to memory addresses outside of the segment where the code is. This is one of the ways to search for global variables. Or read, write memory references to outside of the current function's boundaries, because maybe we are uh, targeting or reverse engineering a software that mixes data and code in the same segments. It's not very common, but it might happen. Also, distinguishing between constants and variables might be done by checking the permissions of the segment. For example, if it is read-only. In most cases, we don't really care. We can post a variable declaration with assigning some specific constant value, like, I don't know, const, star, char, some name, equal, and quoted some string. And the compiler, when we are going to compile, is going to remove that variable and just put the constant in the raw data segment or wherever it is relevant, depending on the compiler. So in opposite to the previous case, this is, however, our task to determine if we are dealing with a constant or a global variable to output compilable source code. I think it is more readable when we are recovering source code to, for example, let's say that we are talking about a printf code, issuing or writing printf and quotes the whole constant, than doing printf, some global variable, and declaring the global variable somewhere. So you have to go to that somewhere part and then check the global variable. I will talk a bit later on about how I have done that in my current prototype, but, well, we don't really care about it. Okay, so finding external functions. There is another thing that we need to do, is to find the external libraries being used and the runtime functions used by your target. For example, let's say that we are representing some piece of software that is using the functions create file A and the function sqrt. So depending on these functions, we will need to add the proper header files as well as the corresponding library files to link with. For example, if it is using create file I, we want to output source code files, including the Windows.8 header file. If it is using sqrt, we need to include the mat.h header, and we also save somewhere that we need to link the mat library into our project. We can actually do it in an easy way. With easy, I mean, what I have done myself was parse the whole /user/include of my home Linux box and parse all the header files that I have in my Ubuntu box at home with clang and extract or generate some huge tables that I have in my prototype that says that function is used or requires that header file and that library file to be linked with. It must sound a bit complex, but it really isn't. It is the easiest part, I believe, of that project. So as I said, header files must be added to the specific source code files we are going to write that are using them. I mean, we don't want, if we know that in some specific file, like, I don't know, main.c, they are using create file A, we want to include Windows.8 in that main.c or cplp source file, but we don't want to include the same header again and again in other parts, in other source files that they aren't using that function or that header file. Okay. More. So finding source files in the binaries. Just this task by itself, I believe, is a well-researched topic. So it can be summarized or can be explained in another way. So how can we guess the object files boundaries and thus the source files boundaries in binaries? Actually, I know one guy that have done some research in this specific area. His Twitter handle is evm_sec. And he has done, at least in Recon, and I don't remember where else, probably in SummerCon, but I don't remember properly, a talk about doing so, which is called a Code Pirates Recovering Software Architecture from Embedded Binaries. So basically, what they do is, when you are linking your project, you first compile your, like in the picture shown here, you first compile main.c to main.o, then matlib.c to matlib.o, etc., etc. And then when you are linking, usually in the order that you put the object files to the linker is how they are going to be in the final binary. They are usually in that same order. And doing magic that this guy is doing, it infers what are the boundaries of the original object files that were used to link together for your final target. So if we have the backend information, we can skip this step. But if we don't have the backend information to determine which function belongs to which object file or source file, we will need to do something like this to determine which source files are in our project and which functions or globals or whatever belong to which specific source file. Okay? More. So finding runtime functions. We also need to find the users of C or C++ runtime functions, but basically to ignore all of them. We don't want to add, for example, libc, start main, or gmon start functions to our generated source code files, because this is something that the compiler, in this case, GCC, adds. Sorry. And we don't want to recover the runtime parts. So the solution to this problem is kind of easy. For example, using IDA, we can use the flirt signatures. And whatever was recognized by the flirt signatures, just ignore. Also, if we have function names, we can also blacklist some of them. But this is a never-ending history because you have to blacklist a lot of functions from a lot of different runtime, from a lot of different compilers. Also, we must let the reverser somehow specify which functions must be skipped or must not. Probably we don't want to use, we don't want to export some runtime functions, but maybe in some specific case, we need to export them. I cannot figure out right now why, but it can be required for some reason. More, finding object hierarchy. So let's say that we have reverse engineered as a target for some time, and we have proper function names, local variables, globals, structs, enums. Now, when writing source code files, we need to know which structs, functions, enums, global variables, etc., are used by each source code. Also, source file, if you prefer. Also, we need to remember that structs, functions, etc., etc., might depend on other structs, types, functions, etc., etc. Let's say that we have some struct A with two fields in something, and then we have a struct B with int, with a field int something, and the second field is struct A field name. We need to have the hierarchy properly to write the struct in the proper order, because otherwise we will have compilation problems. It is pretty much impossible, in my opinion, for big enough projects to write a magical tool that you click in a button and you have full compilable source code. However, you can make it as much easier to get compilable source as possible. And for doing so, this is one of the basic tasks that must be done. We could work around that by adding a lot of external declarations and adding if-def macros, but this is ugly and it's pretty much unreadable, and macros cause a lot of problems. I don't recommend doing anything like that. This is just my opinion. And well, finally, the last step is to just write the generated source code files with all the required dependencies and with the whole hierarchy result, plus the building files. With building files, what I mean is how to build the source code that we just write. In my prototype, for now, I'm just generating plain make files, but we could generate anything. We call generate building files for CMake, Visual Studio project files, for Ninja, or for whatever else that we might want. Okay, the prototype. So since September last year, I have been working on a prototype for now of such a tool. The prototype is an IDA plugin plus IDA Python tool. I call it Source Recoverer. I'm not very original, I guess. Let's briefly discuss about it. So first, the components of the prototype. It is an IDA C++ plugin that I call IDA Unexposed, which is to simply export one function that I need, because the function's prime type and format data to get a compilable representation of global variables, constants, and stuff is not export and cannot be used from IDA Python. So I just export a function called getCdef from a C++ plugin to do so. And then an IDA Python independent script that uses the previously mentioned plugin and does everything expected from a source code recovery tool. Everything that I have been discussing about during this presentation. So how it works? As I said before, it iterates all functions in the binary. It guesses all the source files if possible. I use the backend information when it is available, which is not by default. Or otherwise, I use another IDA Python script that I wrote some time ago, IDA Magic Strings, that tries to determine which functions belong to which source code source files. So this is one of the ways that I'm using in my prototype to try to say this function belongs to main.c. That other function belongs to, I don't know, misc.c, etc. And so I get all the structs, nums, and global variables using IDA for now. Then I decompile all the functions. I write a project file so the reverser can make changes about how the code is being written. And then source code with the dependencies that requires mostly full resolve are written, and a make file for building the code. Also, when something is changes in IDA, only the modified part or source is modified. For example, let's say that we have some function where we have some specific variable name, which is an automatic name like v1, v2, v3, and we want to change to something. Like if we change v1 to option, when we are going to write again source files, we don't want to write the whole project. We just want to write the specific source file where that function that we have changed has changed. This is what it does. And that's it, basically. Let's see some demo. Give me a second, please, because I have to share now my wall screen, and I am still very new to Zoom. Give me a second, please. Just a second. Yeah, desktop sounds great. Okay, so this is my desktop. And let's open now one binary. Okay, so the binary I have opened right now is called CMD scan. It is actually the command line scanner of one antivirus, of Komodo antivirus. It is a very easy to reverse engineer piece of software, and I have many things already reversed here, but I haven't changed too many things. Okay, so what I'm going to do now is to just execute my script, which is that, recover, and see what happens. Okay, it has done everything it needed to do. It has treated first the project file, which is that one, CMD scan. This is the IDA's database name dot recover. We can open it here. Here's it. And well, this is a project file with many things. We will take a look to it later. And it says that it has written the following files in this directory. So we are going to go to that directory. As we can see here, we have the CPP file with all the functions, an auto-generated header file. This file, devs.h header file, is something it created, and then we have the make file that it creates. So this is the first time that we just execute my prototype over this piece of software. It's all failed the first time. Make. Okay. Recipe for target, whatever, it fails. Let's see why. Okay. So in the auto-generated header, it says that we have redefined one struct. Okay. The tool is failing because it's failing to build because we have some redefinition of a struct. Let's fix it in the header file. Okay, yeah. So we want to remove this ones, and we only want to have this specific struct that I have reverse engineered. Save, that's it. And the next part is, it also complains here because the gmon start was not declared. Of course, because this is something specific of GCC and specific of the runtime, we shall not be doing anything with gmon start. So I'm going to check in which function it happened. 78, it says. Let's go to it. Sorry. Yep. 78. And the function is that one. Let's go now to IDA. Here we are. So we don't want to export that function. How can we do that? We open the project file, and we have a section which is called ignored functions. We are just going to add one more ignored function. Okay, and run again. This is incremental, okay? Now we see that it is ignoring that function. It only wrote one source file. Well, actually, the only one that we have for that project, but if we had more, it will only output one, and then we can go again here. Let's do make. Sound file now. Ah, yeah, okay. There is one more function that is failing. Sub, some address. Let's go here. Okay, this function is a thank function. By default, in my prototype, I ignore thank functions. However, as I said, we need interactivity, but because even when in most cases we don't want to export thank functions because they are automatically generated, maybe in some specific cases we won't. And actually, in this case, we want to do so. So what we do is in force as, there is a section called force as in the project file. We just add the function that we want to force to be added. Again, it is incremental, so we go here, we run again. Now we shall have that function here somewhere. It is here. The only thing that I haven't done is to put the reference here in the header file, because the header file is only written once, unless we specify otherwise. Build auto-generated header. By default, it is only written the first time. And now let's go back again. We dump again the source. And then if everything goes OK, now we have working source code that we can compile, and the binary is working. It will not do anything because I don't have here the libraries that Commodore requires, but we just wrote a certain source. We just decompile it, literally, and generate this compilable source code from a binary without too much effort, I guess. 1 second, because I'm going to start again the presentation. Okay. Yes. So the future of this tool. So the current tool is just a quick prototype. All the steps that you have seen I have done myself. Now, for this specific project, solve be done automatically. By now, the quick prototype I have written works, but it sucks hard. It really needs to be rewritten properly. I will most likely rewrite it in C or C++, but well, that's just a matter of taste, nothing else. Supporting Ghidra was considered, but the compiler generates too many constructions that are incompilable and they must be clean. So for now, I will focus exclusively on IDA. Also, it really needs an integrated, reverser-friendly GUI. Right now, we have to manually update the project file, which is a JSON file, but we need a proper GUI to assign functions to source files, select which local types we want to export, which ones we want to ignore, which functions we want to add or to ignore, whatever. Actually, two of the steps that I have done here by modifying and writing stuff in the JSON file, so be done by just clicking somewhere. In the current version, source files are found using one of the following two methods, either using debugging information, dwarf mainly because with PDBs it doesn't properly work for a reason, or using debugging strings containing file paths, like, I don't know, something like assert error in file all the path.c. This is how I try to guess where one function belongs to which source files. In the next version, I plan to implement my own version of the EVNSX algorithm for local function affinity, as he calls it, to try to infer translation units, source files, if you want, boundaries in binary files. And also, this part is anything but easy, is classes recovery. This is a whole project by itself. The idea is to try to find the classes being used in our target, resolve the hierarchy, and finally write the definition of the classes too. It is not trivial, but that will be awesome to have in such a tool, I think. So the prototype will be released at some point this year. I cannot release it right now because I have to clear some problems with my employer regarding the tool. And the final tool, not the prototype, hopefully will be available by the end of this year. But I cannot be sure, and considering that we are living a pandemic, who knows? And well, that's all. If you have any question.
Yeah, thanks for your presentation. So yeah, chat, if you have any question, you can ask them now. But while we're waiting for some questions, I have two questions for you. So the first one is, you say you look at Ghidra and then you kind of quickly gave up. Is it because like the quality of the decompiler is that far behind compared to IDA? Or?
Yeah, well, that's only my opinion, okay?
Because I haven't tried it, that's why I'm curious to know about it.
Yeah, that's only my opinion, okay? But I have find many cases, for example, where some constructions aren't properly decompiled, or they are properly decompiled for reading, but not for recompiling again. I mean, some constructions, you can read them, but you cannot fit them to a compiler and expect it to compile them. No, not at all. However, with Hexrace compiler, I have noticed that I can do so. This is why I'm ignoring for now Ghidra. But, well, the quality of the compiler is pretty good, but I don't think it is as good as the quality of the Hexrace compiler. On the other hand, anything that you can disassemble in Ghidra, you can decompile, which is something that you cannot do with Hexrace. So.
And does it support more platform on Ghidra? Do they have like ARM64 decompiler, or is it only like x86, x64?
So in Ghidra, whatever you can disassemble, you can decompile.
Okay.
That's it. Whatever you can disassemble. It forces you to write a processor specification that is later on translated to P code, and based on that P code is how the compiler works. In the case of Hexrace, it is not like that. You have to write a specific compiler for a specific processor.
I see. And I just so there's a question from Ryan. thanks for your presentation and work. Will you post the slides publicly?
Yeah, of course. The slides will be public. Like I don't know, give me 5 seconds after the presentation.
Yeah. Like most of all the slides from today are gonna be on our GitHub repository anyway. After we're gonna centralize everything over there, like we do for each edition of our conference. So that's good. And my second question was, so your example now was on Linux. Did you try on Windows with but for binary with private symbols with a private PDB to see if you get like some really good results with it? Or because I guess one of the big problems is also like type discovery and type recovery, right?
So yes, I have done, and yes, it works. The thing is that it was easier for me to do the demo in Ubuntu, but yeah, I have done that.
Okay, that's pretty cool. That's awesome. And what about public versus private symbols on Windows? Do you see like a massive difference or not that much?
Yes, there is a massive difference.
That's pretty cool. Nice.
If you have private symbols, it is going to be much easier to recover source code. If you have public symbols, good. It is good to have that information, but still you are going to have to fix many things. The less information that you have, the more work that you have to do manually.
Yeah, because I'm thinking like for like private symbols, I mean, few times on Windows, you know, those symbols have been leaked publicly. So, and what about, is it only for like user mode application, or you can also do it for like kernel drivers? Or
that. I mean,
that's cool.
It doesn't matter. I mean, the tooling rating, it will just output source code. It will write a makefile, supposing it is going to be used in a user-land application, but it doesn't really care about what is the target that you are reverse engineering. It can be a kernel, it can be a kernel module, it can be whatever.
That's pretty cool. Yeah, like Jaziel Spellman in the chat is saying looking forward to the release. Yeah, me too. Well, at least the good thing about the confinement is it gets more like time. You should get more time to focus and to write those tools. You know, usually like it's kind of hard to focus, especially writing such a big tool. You know, on your own. You know, it takes a lot of time. But yeah, I think it's gonna be like really cool.
Well, it takes a lot of time. Yeah. So my current prototype, I started writing it by September last year. It works, but it still sucks. So I will need a lot of time to finish it.
Yeah. But that's pretty cool. Well, thanks for choosing Opcode for like the preview of that new tool. That's really awesome.
Thanks to you.
Cool. Well, I don't think we have more questions in the chat. I don't see any other questions. Is there anything you want to add?
Nothing on my side.
Okay, cool. Well, I guess we're gonna get ready for our next presentation, which is gonna be on Hold My Catnip. I'm bouncing over APTs for the purple teaming from Katie, Jesse, and Andre from Microsoft. Thanks, Joxean. How do you pronounce your name, by the way? Is it Roxin or Joxean?
Joxean or Joxean.
Joxean.
Joxean, yeah.
Okay. I know it for next time. Okay, well, thank you, Joxean, and hope to see you soon.
And, thanks to you. Bye-bye.
Bye.